So we'll start our bootcamp now. So guys, I could see like many of you are students and many are looking for a job. So CFD will be a really great opportunity. So here you will get an idea about open source side of CFD. So I'll start the webinar. So do you guys know like what is CFD? So if you have any idea, please post your idea in the chat box. So I'll be able to see. I'll be able to answer. So one thing you can notice in between the presentation, feel free to post your doubts or any ideas you have in the chat box. So I'll be able to see and I'll be able to answer along the presentation. So this will be the content for today's session. So first I will give a brief introduction to CFD. Then we will compare the different sides of open source CFD tools and commercial CFD tools, and then just an introduction to OpenFOAM tool. Then we will see how a case can be run in OpenFOAM, and then we will discuss two basic cases, a cavity case and airfoil case, and we will compare these cases with commercial software, and then we will check different advanced cases available in journals. So here we have 4 cases, and we will see how the researchers are running CFD simulations in OpenFOAM, and how the results are available in commercial tools, and how the results are matching, whether they are not matching or something. So we will check. So this is regarding CFD. So do you have any idea what CFD is? Please post in the chat box. Okay, someone has mentioned Computational Fluid Dynamics. Great. So it is basically a branch of
sorry to interrupt, Tomu.
Yeah.
I'm seeing that whatever the technical questions Mr. Tomu is asking you guys, you are posting your answers to me, right? So don't do that. What you do is you have two, right, where you are writing your answers. There is a drop down feature, so you will get the 3 names there: Mr. Tomu, Rajiv, and Mehul. So whatever the answers you want to give, right, whichever questions are being asked by Mr. Tomu, please select Tomu name and then reply your answer, so that it will give the visibility to Mr. Tomu and not to us. So Jaya Prakash, Rajnikant, still you guys are basically texting me. You have to click on the drop down feature and select the Tomu's name, and then that answer will go to Tomu. Okay, so let's do that so that Mr. Tomu gets the visibility, because he's asking the question, so you should answer to him. Okay, sorry to interrupt, Mr. Tomu, all yours.
Yeah, sure. So some students have told analysis of forces acting on moving fluid, prediction of fluid flow, finding displacement of particle. So CFD actually comprises of everything. So CFD helps engineers conduct virtual simulations of physical phenomena. So whatever you have said, right? So those are physical phenomena. So fluid moving, some particle moving in a fluid. So CFD helps us simulate those cases using computers. So using computers, we are predicting what is going to happen, or we can predict whatever is available using the historical data. And some situations where CFD is used. So here you can see flow of air around a Formula 1 car. So in F1 races and all, engineers use CFD to analyze how the air is flowing around their vehicle. So they can optimize their designs better, and they can compete in the next round with a more optimized design. And the flow of river when a dam breaks. So it will be helpful in case of to predict what will happen in case a dam breaks. So we will know the path of the river. So how the river will be flowing, so that sufficient escape mechanisms can be put in place. And another one is the sneezing simulation. So here on the right side, you can see the sneezing simulation, which is done. So you might be seeing governments issuing guidelines during COVID, like distance between 2 persons should be kept around 1 meter. So those guidelines are actually based on such case studies. So here you can see when a person sneezes, how the particles are traveling in air. So based on this analysis, they will be able to understand at how much distance these particles will be able to reach, so that they can issue proper guidance to the public. Okay, so CFD in industry. So even though you might think like CFD might be used in automotive engineering or maybe chemical engineering, CFD can be used in an array of industries. So this will include electronic cooling also. So in case of electronic cooling, I can say an example of a processor. So if you have a chip inside your computer, right? So it will be heated. So sometimes the performance of the chip is restricted, so that it won't generate more heat. So how much heat it is going to generate, we can use CFD to predict. So similarly in aerospace and in process industries, in pharmaceutical industries, everywhere CFD is used. So what are the steps involved in a CFD simulation? So this is basically a generic overview. So first you will have a geometry. For example, you can consider an F1 car in this workflow example. So consider an F1 car as a geometry. So then as a first step, you will proceed for meshing. So meshing means you will be dividing the car, the entire model or entire geometry into very small elements. That is called meshing. And then using any CFD software, you will have to set up your CFD simulation, and then the software will be running the simulation. So it will basically solve the governing equations which are governing the flow. And finally, there will be post-processing, where you will analyze your results. So then you can see there is a feedback loop from post-processing to geometry. So in the case of an F1 car, during post-processing, the engineers will be able to analyze what all problems are there with their design, so that they can improve their design. So after post-processing, they will come to geometry phase again. So here they will modify the design of their car, and then again they will repeat the same procedure. So then they will analyze what all advantage they will get with this modified design. So this process will repeat until they have an optimized design for their match. Now for CFD, we have several tools. So there are open source tools and commercial tools. Commercial tools means paid tools. So for example, you might be knowing like there are several students in this bootcamp, right? So they might be knowing about ANSYS Fluent, which is common in engineering projects. So it is basically a commercial tool. So you will have to pay if you want to use the software. Whereas OpenFOAM, as it is mentioned here, it is open source. It is freely available. So there are other examples given, but I think for students, most common software they will be familiar with will be Fluent. Now there are some difference between commercial and open source. So in the case of commercial tools like ANSYS Fluent, it will have a huge license cost. So sometimes institute will be paying ANSYS Fluent a lot of money so that their students can use. But in the case of open source tools, it is free. So whether you are a student or someone who is working in the industry, it doesn't matter. So you will be able to use the software for free. And one problem with commercial tool is that the code is hidden. So whatever simulation you are running, you won't be able to see what is happening in the backend or inside the software, what code is being run. So problem is you will only have your input and your output. You can't change what is happening inside. So if you want to modify some part of the CFD simulation, apart from your geometry or your setup key or whatever limited options are available in the tool, there is nothing you can change. But in the case of open source tool, the code is publicly available. So you will be able to change some part of the code and you can check how your results are varying. So you will be able to use the most optimized code. But one advantage with commercial tools when you're a student is you will be able to learn the tool very easily. So if you want to run a simulation, you can set up the simulation and process the results in a short span of time. But in the case of open source tool, mostly you will have to spend a lot of time initially on learning the tool. Now, using open source tool in industry. So even though using commercial tools will give you some advantage, there are a lot of good things for companies if they were to use open source tools. For example, first would be the cost. So companies will be always looking for cost cutting. So where they can reduce the cost so that they can use that money for uh, other purpose. So that is one of the advantage, savings for companies in terms of license cost. And in case of commercial tools, there will be a limit. So they will give you some limits on on how much processors you can run, or in how many PCs you can use the software. There will be always limits, and if you want to increase the limit, you will have to pay more. But in the case of open source tools, there is no limit. So you can run the case in any number of CPUs you want, any number of systems you can use this software. Now, regarding different industries are there, as I have mentioned before. So in commercial tools, once they buy the tool, there will be a limited number of options. So the number of industries that will be able to make use of the softwares will be limited. But in case of open source tool, they are giving you the code for free. So what you can do is, whatever industry you may be in, you can modify the code as per your requirement. So you can develop new methods, new models, new solvers. So according to your industry, you can modify the code and use. Now, OpenFOAM. So I have mentioned a couple of open source tools before, but the most common open source CFD tool that we are seeing being used both in academy and industry is OpenFOAM. So OpenFOAM stands for Open Source Field Operation and Manipulation, and it is currently owned by Open CFD Limited company, and it is available for both industries and academia. And the code is basically written in C++ language. So most of you guys might be knowing C++ programming language. So this code is written in that language. Now, some features of OpenFOAM. So in case of CFD workflow, I had mentioned one of the steps was meshing. So meshing is you are dividing your geometry into multiple small elements. So in the case of OpenFOAM, you can you get the meshing utilities, block mesh and snappy hex mesh. So you can use block mesh for simple mesh generation, and complex meshes can be generated with snappy hex mesh. And OpenFOAM also supports a variety of solvers. For example, multi-phase, conjugate heat transfer. So conjugate heat transfer means the heat transfer from solids to fluids. So for all these cases, there are different solvers available in OpenFOAM. And to process the results, which is the last stage in CFD simulations, you can use ParaView, which is packaged with OpenFOAM. ParaView is a separate open source tool, but it is packaged with OpenFOAM. So right from meshing until your post-processing of data, OpenFOAM can be used. Now we will see a sample OpenFOAM simulation. So this is run in OpenFOAM version 7. So this is a statue that is, it is called a Moe statue. So this statue is located on Easter Island. So here we will check whether we can find the force acting on this statue due to wind. And the model for this statue is freely available open in the public. So if you check this website 3dcontentcentral.com, you will be able to download this model. So I have so here we have downloaded that model, and the actual dimensions of the model is as shown: 4 meter by 2 meter by 2 meter, and the model was scaled down. So so a CFD simulation will require a good computer to run. So in case you have a computer with low performance, you can always scale down your model to a small size. So here we have scaled down to 1/10. So we are using the scale down model for our simulation. So this is basically the CFD case setup. So here you can see the case setup that is in ParaView. So here we can see an inlet air, and then the statue at the middle, which is around 0.86 meters. Then we have a domain which is enclosing this statue, and there is an outlet. So here we have a wind blowing along the Z direction. So so we'll be checking how much force this wind acts on this statue. Okay, so first we are using here snappy hex mesh, not block mesh, because here the model itself is slightly complex, so we can't use block mesh in this case. So this is the mesh that we have generated. So here you can see in the statue region there is no cell, because there is no flow of air through the statue. That's why there are no cells inside the statue. And then you can see finer mesh close to the statue, because the flow of air will not be uniform close to the statue. So we will have to capture the movement around the statue. So we will need to use smaller cells around the statue. And then behind the statue itself, you can see a more refined region. So this is to capture the wake region. Wake region is the region behind the statue, which is one of the most interesting areas, regions of interest in a CFD simulation or a flow simulation. So the number of cells here we can see 7 lakh. So after meshing, your CFD domain consists of 7,49,000 cells. Okay, so here we have assumed a 9 meter per second air. So this is assuming a wind speed of 20 miles per hour. So if we have a wind speed of 20 miles per hour, it will be close to 9 meter per second. And then we have mentioned the gauge pressure is 0. So whatever pressure we are going to calculate here, it will be relative. So then we have no slip walls on the statue surface. This is based on the boundary layer theory that you might have learned during your studies. So whatever air particles are there, it will be fixed to the statue surface. That's why we have to give boundary condition as no slip or 0 absolute velocity. Now the domain walls are the walls of this and this cuboid that I have shown. So it has been given the boundary condition of symmetry to avoid any influence of wall effects. So once we have set up the boundary conditions and defined the constant values, so constant values in the sense the viscosity of air, which is considered to be a constant in this case. So once we have defined all these values, then we will be selecting the solver and discretization schemes. So this will be these are actually topics of a greater discussion. So it can't be included in this bootcamp. So once we select all these things, then we can run the simulation. So usually we will be running the simulation for a specified number of iterations. But how do we know when the solution has converged? So how do we specify the number of iterations? So that is given by the residual plot. So suppose we are giving 1000 iterations, then we will check the residual plot. So if the solution is converged before 1000 iterations, we can stop the simulation. So this is the residual plot we obtained from this simulation. So here you can see for the different fields here. So UX, UI, UZ are the components of velocity. So the residuals essentially means the error between successive iterations. So between 2 iterations, the error is seen to be reduced, but you can see after 200 or around 250 iteration, it has reached the lowest value. So after 250, it is just fluctuating between 2 values. So this is actually a sign of convergence. So if we see such a trend in your residual plot, then you can stop your simulation. So here the plotting is done with GNU plot. And the total time it took to run this 500 iterations was around 2 hours. So once we find that the solution is converged, now you can analyze for the parameter of your interest. So here we were actually trying to find out how much force is acting on the statue. So the total force will be the sum of viscous and pressure forces. So here we could find that both the forces. So here I have plotted the values also. So you can see the value also is converged. So after around 100 iterations, you can see both the values are fluctuating around 1 point. So this is also another sign of convergence. So in a CFD simulation, you have to check for different signs of convergence. You can't say that your solution is converged based on one plot or one result. So here we got around 10 Newton force acting. So that is for the scaled down model. So we have reduced our model size. So when we convert this force to the actual model, it will be around 10 kilonewton. So around 10 kilonewton of force will be acting on the statue when a wind at 9 meter per second is flowing over it. So these are the velocity and pressure contours. So this is one slice or cutting plane I have taken. So here you can see the velocity of air around the statue. So here you can see above the statue, you can see a red region. So there is a high velocity. So if you see the chart or the color bar here, you can see around 13.6. So 13.6 meter per second, you can see above the statue. And behind the statue, you can see a wake region. So the air will be flowing in a recirculation fashion behind the statue. Now we will see the pressure contour. So you can see in front, there is a large red region with a very high value. So that is because the wind is blowing towards the front side of the statue, and hence it is getting blocked by the statue. So there is a buildup of pressure. So this is usually called a stagnation region, and the pressure is usually called stagnation pressure. And then we have noticed a high velocity flow above the statue head, right? So here in this pressure contour, you can see a green region there. So you might have like learned during your studies. So as the pressure decreases, velocity increases. So in this case, you can see as the velocity was very high, the pressure is very low in this region. Now we can just compare the results from OpenFOAM and ANSYS Fluent. So let's run two cases in both OpenFOAM and ANSYS Fluent. So the first case would be a cavity case. So this is the cavity case. So here you have a fluid surrounded by a wall. So three sides of the fluids are surrounded by a fixed wall. And the top wall is moving at 1 meter per second towards the right. So this is our case setup. So this is an isothermal case, means there are no temperature variations that we are considering in this case. And incompressible means the density variations are also neglected. So we are assuming that the fluid always has a constant density. And then this is a two-dimensional case. So you can see in XY plane, we are able to view this case. So this is the mesh that is used in OpenFOAM and ANSYS. So we have used the same mesh so that we can compare the results in both the software. So here we have divided our domain into 400 cells. So along each direction, we have divided the length and breadth into 20 cells. So in total, we will get 400 cells. And on the right-hand side, you can see the boundary conditions. So here also, you can see there is no slip condition. So in the statue case, we were using no slip condition on the statue surface. So in this case, we are using the same for the fixed walls. So for at the close to the fixed walls, the fluid will be in rest. So these are the velocity contours. So you can see we are getting almost the same result in both OpenFOAM and ANSYS Fluent. So here we have scaled our results to the same scale. So we have shown the velocity from 0 to 1. So 1 will be 1 meter per second. We had mentioned is the velocity with which the top wall moves towards the right. So if you can see, we are getting the red region on the top side only, because that is the only region which has 1 meter per second of velocity. So towards the bottom, you can see it is more blue region is there, which means the velocity is closer to 0. So at the bottom, it is almost 0. So this is how, if you plot the velocity vectors, you will see a diagram like this. So it shows the direction of the velocity vector. So you can see how the fluid is moving. So inside this cavity, you can see the fluid is rotating in actually. So it is flowing in a circulation zone. So on the top, the fluid is moving towards the right. At the bottom, it is moving towards the left. So this is how you can expect the results if you actually do this experiment. So these are the pressure contours. So from the pressure contour, you can see towards the left, we have a blue region. So it is showing a pressure of around minus 4.4. So it is a low pressure region. Pressure is actually negative. And at the right side, you have a red region. So the pressure is positive. So you have a negative pressure region and a positive pressure region. But there are not much fluctuations in pressure at the other regions, as you can see. Now we are plotting the velocity along this line. So you can, on the right hand side, you can see a line, a red line. So we are plotting the magnitude of velocity along this line. So you can see that the value. So here we have plotted the result for both OpenFOAM and Fluent. Now you can see both plots coincide. So which means that the results are almost same in both the tools. Now we have our second case, which is an airfoil. So you might know the airfoil shape of the aeroplane. So the aeroplane wings are made in such a fashion to generate lift. So this would be like a cross section of an airplane wing. So you can see the section here, and the air is flowing at an angle of 8 degree. So this is basically called the angle of attack in airfoil simulations. So this case is also an isothermal case, and incompressible case, and two-dimensional. So these 3 points are the same as in the previous case, but the only difference is this case the flow is not laminar, it is a turbulent. So if you might have studied about Reynolds number. So if we find the Reynolds number in this case, it is 9 into 10 raised to 7. So which shows that the case is a turbulent case. So in the same fashion as before, we are mentioning the surface of the airfoil as no slip. So the whatever air particles are there, it would be sticking to the airfoil surface. And here we have given a velocity of 26 meter per second. Now this is the mesh used in both the tools. So on the left side, you can see the entire mesh, and on the right side, you can see the zoomed in version. So whatever is shown here closer to the airfoil, so the mesh will be looking like this. So the total number of cells in this mesh will be around 10,000. And you can see the airfoil is very small compared to the entire mesh. This is because we want to avoid any effect the boundaries will have on the flow around the airfoil. That's why we have taken the boundaries very far away from our airfoil model. Now you can see the pressure contours of both the tools. So here you can see the red region is larger in ANSYS Fluent. But the blue region is smaller in ANSYS Fluent. So blue region essentially means lower pressure. So in this case, it is negative pressure. So even though overall profile looks similar in both cases, there are some small differences we can notice. And this is the velocity contour. So if you can see, this also looks very similar. But if you look closely in ANSYS Fluent, at the tail region, you can see a larger blue region. So the color is more bluish in the tail region. So it shows that the velocity, lower velocities are noticed in ANSYS Fluent predictions. But if you consider the leading edge or the front portion of the airfoil, there are not much differences. So both ANSYS Fluent and OpenFOAM predicts almost same velocity around the front, but there are some differences around the tail region. So if you plot the pressure coefficients, so if you know what is pressure coefficient, so if someone knows what is pressure coefficient, please post in the chat box. So pressure coefficient is basically showing us the pressure with relative to the free stream pressure. So here you can see we are getting negative values of pressure coefficient along the bottom side of the airfoil, which means that comparing to the free stream pressure, we are having lower pressure at the bottom side. Now, if you compare the values, you can see we are not getting a coinciding plot as we have seen in the cavity case. Here we are having some difference, but still, if we calculate the deviation, so or the difference in values, so around up to 5% difference is noticed in OpenFOAM and ANSYS Fluent. Now we will check with some advanced cases, and right now we have only compared OpenFOAM with ANSYS Fluent. So we will check. There are multiple CFD tools apart from ANSYS Fluent. So we will check how our results are matching, or whether they are matching or not with other CFD codes. So first is a case of ammonia mixing with air. So both ammonia and air are in gaseous phase. So this is the case setup you can see. So air is entering from the left side and ammonia is entering from the top side. So this is the main pipe and there is a mixing module at the right side. And after mixing, we have ammonia air mixture at the right side. And you can see there is a dotted region in the middle. So it shows an injecting pipe and there are some holes in the injecting pipe. So ammonia is mixing with air after coming out from the injecting pipe. So these are the mass fraction plots. So mass fraction means a value of 1 means it is pure ammonia, and a value of 0 means there is no ammonia, so it will be air. So you can see both plots are similar. So there are not much deviations we can see. So this zigzag region you can see around the middle is the mixing module. So you can see the contours look very similar in the mixing region itself. So we have matching results. Now this is a plot of ammonia mass fraction at one plane. So that plane is shown on the right side. So you can see 10 planes we have shown here after the mixing module. So the left side plot is for the ammonia mass fraction as at the last phase, the last plane. As you can see, the blue arrow is showing the last plane. So you can see here, like OpenFOAM shows a larger region with a value of 0.16. So 0.16 value means there is perfect mixing. So OpenFOAM is actually showing us that it is predicting perfect mixing. But in the case of ANSYS Fluent, even though the contours look same, the value is not 0.16. So 0.16 value region is actually smaller in ANSYS Fluent. Now here we can see the turbulent kinetic energy plot. So if you see, there are 10 points on this plot. So 10 points, each point represents a single plane in the diagram shown on the right. So turbulent kinetic energy value at a single plane is evaluated. And then similarly, we are finding the values at 10 different planes and then plotting. So you can see there are some differences. So overall, the trend is in both the tools, the value is decaying. But still, OpenFOAM is showing us higher values. So we have noted earlier that more mixing is shown in OpenFOAM. So this could be one of the reasons. So we are having higher turbulent kinetic energy in OpenFOAM. So that could be one of the reasons why we are having higher diffusion or higher mixing in OpenFOAM. So from this work, the publishers have mentioned that the ANSYS Fluent is able to solve meshes with poor quality. So in every CFD simulation, we will have to check the quality of the mesh. So here they have seen that ANSYS Fluent is able to accommodate meshes with very poor quality or high skewness. But when they tried the same mesh in OpenFOAM, they did not get results, or it was diverging. So there was instability. So you can use poor quality mesh in ANSYS Fluent, whereas you will have to improve your quality if you want to use the same in OpenFOAM. And in this case, with injecting pipe and mixing module, we have seen that OpenFOAM gives us results with higher mixing or higher diffusion. Now, the authors also did the simulation without mixer or without the mixing module or the injecting pipe. And there also they have noticed that OpenFOAM exhibits more diffusive results, but ANSYS Fluent results are more convective. So the particles are getting transported to greater length before diffusion. Now, this is a case of 2dB benchmark case. So 2dB means a two-dimensional bump. So you can see the bump diagram in the middle. So here the authors have simulated flow of air over this bump and compared the results with OpenFOAM and star CCM plus. And in order to validate the results, they have compared it with NASA results. So NASA already has published the results using their own solvers, CFL 3D and Fun 3D. So they have the results available with this software, with these tools. So here they have compared star CCM plus and OpenFOAM results with NASA code results. And they have considered 3 turbulence models, which are SA, SSTM, and SST 2003M. So SA is actually called the Spallard-Talmaras turbulence model. Now you can see the entire domain in this diagram. So you can see the bump at the bottom. So the x coordinate of the bump will be from 0 to 1.5. So there is an inlet and there is an outlet, just like our previous case. So this is the mesh that I have used. So you can see, so closer to the bump, they have a more refined region. So, and far away from the bump, you can see the mesh is like the cell size is very large. So that is because the flow won't be having much fluctuations in this region. So there is no need to have a smaller cell far from the bump region. So these are the mesh sensitivity analysis. So mesh sensitivity analysis means we are comparing results from multiple mesh. So we are making multiple measures for the same domain, and we are comparing some value. So here they have compared the skin friction coefficient or CF value. So you can see the CF value for 3 different x coordinates, and the results are for 3 codes. So one is OpenFOAM, one is CCM plus, and the other two are NASA codes. So as you can see, in OpenFOAM, convergence is similar to NASA codes. So you can see the OpenFOAM plot is actually moving this similar way as NASA codes. So in order to analyze this graph, you can move from the right to the left. So the right means the cells are larger or you're having a coarser mesh. And on the left, you will have a finer mesh. So in all the plots, you can see star CCM results are deviating significantly from other codes. So this means that in when we are using coarser mesh in star CCM plus, your results are actually not agreeing with available results. So, but when you use a very fine mesh, or the finest mesh in this case, you are having results matching with your NASA results. So once they have conducted this grid sensitivity analysis, then whatever mesh is at whatever mesh we are getting good results. So in this case, it will be the finest mesh. So all the simulations that they want to run will be done on this finest mesh. So this is the CF and CP. So CP you might have already known, like it is mentioned in the previous case. So same CP only, coefficient of pressure. So those values are plotted here. So here you can see all the codes show similar results. So there is a good agreement with NASA results. So this is the eddy viscosity plot. So here you can see some difference. So the first plot is actually the normalized eddy viscosity along the vertical line. So the vertical line is above the bump peak. And then there is maximum eddy viscosity along stream direction. Now you can, if you compare the results, both tools are over predicting. So both OpenFOAM and star CCM plus are predicting higher values compared to NASA. But the difference is around 4% only. Now the same procedure is followed for the other 2 turbulence models, the SST and SST 2003M. Now finally they have arrived at the following conclusions. So as we saw earlier, good results are obtained only at the finest grid, and star CCM plus data deviates significantly on coarser grids. And also star CCM data is showing some divergence at the domain boundaries, even when we are using finest grid. And both the tools predict the maximum eddy viscosity value. Now we will see one vehicle drag coefficient using OpenFOAM. So does anyone know what drag coefficient is? Please post. So drag coefficient is basically a number. It is representing how much aerodynamic our vehicle is. So every vehicle manufacturer will be running these simulations, and they will be determining how much drag coefficient their vehicle has. The lesser the drag coefficient means, the better the aerodynamics of the vehicle. That means that vehicle will have a higher fuel efficiency. So in this study, they have considered three models: a notchback, fastback, and estate back models. And you can see the notchback geometry here. So they have compared the drag coefficient results. So here they have done the simulation in OpenFOAM, and they have an experimental and another ANSYS Fluent results to compare with. So this is the case setup. So there is the vehicle similar to our statue location in our first case, and then this is the entire domain. Now we can see the results in this slide. So here we have estate back, notchback, and fastback results. So first one is the experimental CD. So with the experiment, they found the CD values as 0.328, 0.278, and 0.230. Now there is another study conducted by another group. So they have conducted the simulation in ANSYS Fluent. So these are the ANSYS Fluent values. So unfortunately, they don't have the result for fastback model. That's why there is a dash here. And then there is OpenFOAM results. So as you can see, all the codes show similar results. Now, if we compare our OpenFOAM results with that of experiments, so this is the equation that we are using. So you can see for estate back, the difference is only 1.8%, which means OpenFOAM is actually predicting the results very close to experiment values. But in the case of fastback, it rises to around 7%. So these are the conclusions that we have. So we have so they have meshed the domain using snappy hex mesh, which is available in OpenFOAM, and the turbulence model they have used is k epsilon. And as we have seen in the previous slide, the values are very close. So 1.1 to around 7% error between the OpenFOAM results and experiments. And they have also found the rare wake structure, so which is the structure of airflow behind the vehicle. So it shows good agreement with whatever was reported by Wang. And then the CD predictions or the drag coefficient predictions are comparable with Fluent predictions. Now this is another case of an actual vehicle. So this is the Volvo SIT model vehicle. So you can see the geometry of the vehicle. So here also it is an aerodynamic simulation. So this is the mesh that they have used. So you can see the cells are very finer, closer to the vehicle, and there is a refinement behind the vehicle also, because this is another region of interest for CFD simulations. So the air will be flowing from along the X direction from left side to the right side. So you can see the results here. So this is the velocity field. So you can see similar results in both OpenFOAM and ANSYS Fluent. So as you can see, the wake region or the region behind the vehicle is similar in both the software. But if you see this region above the hood and above the trunk, so this region is larger in OpenFOAM, but whereas in Fluent you can see the region is very small. So this result shows that there is a separation, more separation in OpenFOAM, whereas less separation in ANSYS Fluent. So this is also a velocity field, but at a plane which is cut at the belt line. So you can see this is the hood region of the car, and then this is the trunk region. So you can see there is a slight difference in data at the rear end. So you can see there is a change or difference in the structure behind the vehicle. So there is a small difference in the values. And if you check the mirror side also, you can see there is a separation region for the mirror. So mirrors are actually increasing your drag coefficient. So in this case, you can see in OpenFOAM, you will have a longer region. So it is very short in ANSYS Fluent, whereas it is very long in OpenFOAM. So this means that the separation in OpenFOAM is larger. So similar to all our previous cases, here also we are checking the pressure coefficient values. So here we have plotted the pressure coefficient values over the surface of the vehicle. So you can see the contour looks very similar in all the regions except the front tire. So in the front tire region, you can see in OpenFOAM there is a darker blue region, whereas in ANSYS Fluent it is more lighter. So darker region essentially means a very lower value. So this essentially means OpenFOAM predicts a stronger separation. So this is the same thing that we have noticed in the previous slide. So in OpenFOAM at the mirror region, it showed a higher separation. So in front tire region also it is showing higher separation. So the final conclusion that we have is almost similar results in both tools, OpenFOAM and ANSYS Fluent. But one advantage that we get OpenFOAM is we can change almost every control parameter. But ANSYS Fluent is able to handle coarser mesh or less number of cells with good results. But if we are using the same coarser mesh in OpenFOAM, we are getting diverse result. So what we can assume is that if we provide more refinement to the mesh in OpenFOAM, then we will be able to match the results with ANSYS Fluent. But a higher refinement will always lead to a longer runtime. So now if you want to work on an actual vehicle simulation, there is a resource available. So the Technical University of Munich has collaborated with some vehicle manufacturers, and they have developed a model named DriveAir. So the model or the geometric model or the 3D model is available on this website. So if you check this website, you will be able to freely download this geometry model, and you can run your CFD simulation in any tool. So for example, in OpenFOAM. So you download this model and then run the simulation in OpenFOAM, and you can validate whether your results are correct or not. So based on this DriveAir model, there are several journals published, and there are some experimental results available on this website. So you can check whether your predictions or whatever predictions is getting from your CFD tool is correct or not. So you can compare your results with the experimental results. So just like how we have compared between different tools in this bootcamp. So similarly, you can check. So that's all about this bootcamp.